In this video, we are going to discuss question 3 and question 4 of question paper 4-2 of the examination series 9701 chemistry Feb March 2024. In our earlier video, we have already discussed question 1 and 2, and so let's go ahead with question 3 and 4. So here is question 3. It says iron is a transition metal in a group 8 of the periodic table. Now this question is about transition metals that shows, and let me be very clear that in each and every question paper 4, the transition metal chapter carries a very good weightage, that every year fixed there are about 15 to 20 marks questions asked in this paper. Let's see how many marks they have asked about, but then this chapter is very important and carries a good weightage. So let's go ahead. You also should prepare it well for the examinations of the question paper 4. Yeah, here is sub question A with 1. Explain why iron has a variable oxidation states. Now any transition metal has a variable oxidation state. It's only because the 4s and 3d orbitals are very close, their energies overlap. So let's write that the energies or energy levels, also you can write, so energy levels of 3d and 4s orbitals, 3d and 4s orbitals of iron you can specify, but even if you don't specify iron, it applies to all the transition metals, so it's okay. I'm not mentioning here. So energy levels of 3d and 4s orbitals are similar, and their orbitals overlap. Orbitals, as their energies are similar, the orbitals are overlapping, and so the electrons can be removed from both these orbitals, that is 4s and 3d, and that's why they have the variable oxidation state. But as we have limited space here, it carries 1 mark. Only the mentioning of similar energies is enough for us. Let's go ahead with the next part. It says complete the shorthand electronic configurations of Fe and Fe3+. Now Fe has electronic configuration of 26. So because of that, the argon, and that is argon, it's till 18. So after 18 we are left with 4s. We'll fill up 4s first with 2, that is rounded up with 20, and the remaining electrons goes in 3d, that is 6 electrons. So here is Fe. Now for Fe3+, we need to remove 3 electrons out of it, and the electrons goes out of 4s first. So if we remove 2 electrons, 1 more electron from 3d, and so we are left with 5 electrons and 3d orbitals. So we have argon 3d5. That's done with first part. A part is the B part. An aqueous solution of iron ferric nitrate, that is FeNO3 thrice, contains the complex iron H2O6 FeH2O6 3+. When the solution of KSCN aqueous and FeH2O6 3+ are mixed together, a color change is observed. The red complex FeH2O5 SCN2+ forms. Define the complex. Now if you look here, this is called the complex, or this one is also called a complex. Now if you have a look at this, what's there? There is a transition metal plus surrounded by the ligands with the charge. The complex can be neutral also. So how are we going to define a complex? It can be a molecule or ion, with a transition metal ion, surrounded by ligands. So that's how the complex is defined. The second part, state the coordination number of Fe in FeH2O6 3+. Now how many coordinate bonds does the Fe form here? 1 with each water molecule, so there are 6 coordinate bonds, and that's why the coordination number of Fe is 6 in this complex. The HOH bond angle in water is 104.5 degrees. Suggest the HOH bond angle in FeH2O6 3+, and explain your answer. To understand this, let's first understand the structure of water. Here we have OH, and on the oxygen we have two lone pairs, and that's why the angle is 104.5. The reason being is that the two lone pairs repulsion is much greater. Now when this forms a bond with Fe, one of the lone pair is donated as to the Fe to form the coordinate bond, and so only one lone pair is left on the oxygen atom. And now if you have a look, if you recall the geometry and the structures of the other molecules from the bonding chapter of AS, you'll realize that the ammonia has a similar structure where it's having the three bonds with one lone pair. Now if you recall, if you try to compare the structure of these complex and ammonia, it's going to be similar. Why? Because O has two hydrogen bonds and one bond with Fe. So similar structure as ammonia with one lone pair on oxygen, similar structure. So you can see that the bond angle of ammonia can be similar to this complex, and so I'll write here as 107 degrees. Why? Because the angle of ammonia here is 107 degrees with the trigonal pyramidal structure. So explaining here will be similar, that the lone pair, one of the lone pair, I'll write one of the lone pair of oxygen, is used to bond with Fe. You can write Fe, or even you can write Fe3+, that doesn't make any difference. And so the lone pair repulsion, or the electron repulsion, lone pair electron repulsion decreases, which increases the angle, of the water molecule. And so this is explanation about it. Let's go ahead with the next part. Here it says, explain why ion complexes are colored and it carries 3 marks. Now this is a fixed question asked in many of the question papers. You will see whether it's an ion complex colored or all the transition metal complexes are colored, whatever, the explanation goes same. So let's start with a similar explanation which can be used every time whenever they asked about the transition metal complexes being colored, is that when a transition metal ion bonds with the ligands, the d orbitals are non-degenerate. Now non-degenerate means they don't have a similar energy levels. They are non-degenerate orbitals. And when the white light passes through it, when the white light passes through the solution, passes through its solution, the electrons use some of its energy from visible region of the white light. So here we need to mention it, visible region, to jump from lower energy to higher energy level, and the part of white light transmitted through gives the color to the complex, gives the color to the complex. I'm ending here as the line also ends, and my explanation is almost over here. So here is what we explain in the 3 marks. Okay, so in the 3 marks you need to mention that there are non-degenerate orbitals for the metal complex when it bonds with the ligand, and then the electrons jump absorbing some part of the white light, and the third part is that the transmitted part gives the color, or you can say the complementary light of the white gives the color. Okay, the next part says the aqueous solution of complexes FeH2O6 through plus and FH2O5SCN are different colors. Explain why these complexes are different colors. Okay, here what's the difference? You can see that there is 6 ligands of water, and here there are 5 ligands of water, and the remaining third one is a different. Now what difference does this make? The difference in the energy level, that is E, different in the energy between the 2 d orbital levels. As we have said, the d orbitals are degenerate, that is of 2 different energy levels. So the difference between the 2 energy levels is delta E. We could draw the structure. If you remember, we draw the structures like this for the octahedral complex. So this difference in the energy of the 2d orbital levels is delta E. Now for the 2 different complexes, this delta E is different. Now when is this delta E different? Whenever the transition metal is different and the ligand is same. Transition metal differs, delta E differs. If the ligands differ, delta E differs here. So these are the 2 factors which makes this delta E different. So here if we explain, we can say that the delta E difference, that is energy difference, is different for 2 complexes, is a different for the 2 complexes, different for the 2 complexes, because of which, so the energy absorbed by electrons, from white light, okay, electrons from white light is different, from white light is different, so color differs, is different, so color is different, as simple as that. So we don't need to give a detailed explanation here, just the difference in the delta E to be mentioned, and so the energy absorbed is different. Let's see the next part. Next part is question C. So question C says table 3.1 gives values for the stability constants K step of different complexes of iron, and here are the complexes given and the stability constant values given. Let's go ahead with the sub question part 1. We'll go through the table later on wherever it is required, and the stability constant values are important. Here the question says this is a complex and it can form when H3PO4, that is phosphoric acid, reacts with the hexahydrated iron complex. So write an equation for this reaction. So obviously we know that this and this is the reactant and this is one of the products. So let's start with that. Fe, that is H2O6, right? And the bracket charge, the whole complex charge is 3 plus. So here you can see that the charge of Fe, that is iron, should be 3 plus. And the next reactant is H3PO4, that is phosphoric acid, and the main product is H2O5, and then H2PO4, and the charge of the complex, whole complex, is 2 plus. Now let's understand what has actually happened. Here we have H3PO4 which has turned into an anion H2PO4 minus. So here we can write an equilibrium reaction. Let's understand what has happened. H2PO4 has been formed. Now H2PO4 has been formed, then we can say that this is an anion and H plus is released out, and this has acted as a ligand for this complex. So H2PO4 has been added as a ligand, and that's the reason that the charge of the complex changed from 3 plus to 2 plus, because the charge of the ligand is H2PO4 minus. So minus 1 and plus 3 of Fe turns out to be the overall charge of 2 plus. So now if H plus is released out, and the next is that one of the H2O ligand, water ligand, is released out. So together with one of the water ligand and H plus, it's going to form a byproduct of hydronium ion, that is H3O plus. So this is going to be the byproduct, and this is how we write the equation. Now it's written, write an expression for K stability of FeH2O5SCN2 plus and give its unit. So let's see what information about SCN ligand is given earlier. Here we could have seen that HKSCN is added to H2O6 3 plus, and that is how the ligand is formed, and then we have to write the K stability value of this. So if we write an equation for this, and I should write it as HFeH2O6 3 plus SCN minus, that gives FeH2O5 SCN, and the whole charge is 2 plus, and 1 H2O is released out. So this is how the equation is, and if this is the equation, then the K stability value should end up with the product on the numerator first. So FeH2O5 SCN, and the overall charge is 2 plus, and the other product is water, which is a liquid, and it need not to be mentioned in the K stability expression, so we are not writing it in the numerator. And at the bottom should be the reactants. So the reactants are FeH2O6, overall charge is 3 plus, and the next product is SCN minus. Next reactant is SCN minus, and the concentration of both has to be the product. So here is a product, so no addition sign, 3 plus is just the charge. So this is how we'll write the K stability expressions. And if we talk about the units, then for this, moles per dm cube in the numerator. Denominator we have mole square dm power minus 6. This is how we'll write, because there are two species with the concentration, so both of them, mole per dm cube, ends up with mole square dm power minus 6. So simplifying this, we get mole power minus 1 and dm cube. This is how we'll simplify it. So the K stability expression is given, and the units are also given. If we go ahead with the next part, it says use the stability constant data in table 3.1 to calculate the value for the equilibrium constant Kc for the following equilibrium. Now if we find out the Kc expression, again the numerator is going to be the product, then H2PO4 minus, and the denominator is again H2O5, H2PO4, again 2 plus charge. So if we have a look, let's have a look at the stability constant values given here. Okay, the SCN values has 1.3 into 10 power 2. And now if you have a look, SCN values is the on the product side, so that value has to be on the numerator. So numerator is having the value 1.3 into 10 power 2. So 1.3 into 10 power 2 divided by the reactant. Now reactant has a stability value of 5.9 into 10 power 1. So let's write that 5.9 into 10 power 1, and if we calculate, it is 2.20 Kc value, and you can see that the units won't be there because it will get simplified to 0 units, no units. So value of Kc is 2.20. So I think question 3 has ended here. Let's go ahead with question 4. Okay, question 4 says ruthenium and osmium are transition metals below in iron in group 8 of the periodic table. Two different complex ions X and Y can form when anhydrous ruthenium chloride, that is RuCl3, reacts with water under certain conditions. Now X and Y are octahedral geometry. Aqueous samples of X and Y react separately with an aqueous AgNO3 and different amounts of AgCl are precipitated. Now 1 mole of complex X produces 2 moles of AgCl. 1 mole of complex ion Y produces 1 mole of AgCl. And the question is, complete table 4.1 to suggest the formulae for X and Y. Now understand that X and Y are formed from RuCl3 which reacts with water. That is ruthenium chloride RuCl3 reacts with water. Now understand RuCl3 is there, that shows that the ruthenium has 3+ charge, and if it reacts with water it is an octahedral complex. So if it is an octahedral complex, it has to have 6 ligands. Now out of that 6 ligands, how many are water and how many are chlorine, that we have to decide. Now if it's reacted with silver chloride, 1 mole of complex ion X produces 2 moles of AgCl. 2 moles of AgCl, in the sense we need to understand that the complex should be octahedral, so 6 ligands. Okay, out of that H2O should be 5 and 1 should be chlorine. Out of the 3 chlorine which were here, 1 chlorine stays with the complex and the 2 chlorine is like an ionic compound form. So you can write it like this way. So when AgNO3 reacts, these 2 chlorine will react to form 2 moles of AgCl. That's how it works. So the complex should be, X complex should be this one, and so we write the formula as Ru H2O5 Cl, only 1 Cl ligand, so total of 6 ligands. Now if you work out the charge, ruthenium is having a 3+ charge in this reactant. So out of that, if chloride ligand is there which is having -1 charge, so the overall charge will end up with 2+. Similarly, if 1 mole of AgCl is formed, that is silver chloride is formed, that should be that opposite here. So ruthenium then in that case should have water ligands S4 and 2 chloride ligands, and the 1 chloride ligand should be outside as an ionic compound formed, and that's why only 1 mole of AgCl is formed. So if we now work out the overall charge, this should be +1 only. So this is how we have worked out the formula, and the formulas of the complex ions X and Y are written here. Okay, let's see what's next. Okay, both complexes reacts with an excess of bipyridine BIPY to form a mixture of 2 stereoisomers of this given. So this is the BIPY, bipyridine. You can say it's a kind of ligand, bidentate ligand. Here it's given, it's in bidentate ligand. So draw 3-dimensional diagram of the 2 stereoisomers of this and use this as to represent the ligand in your structures. Now you're supposed to draw the 2 stereoisomers with a bidentate ligand, and you know it's a bidentate ligand. Ruthenium forms octahedral complexes. So obviously the stereoisomers has to be optical isomers, and let's start drawing a 3-dimensional diagram. 3-dimensional diagram is specified here. So you need to have the bold lines and dotted lines. So obviously the front 2 lines has to be the bold lines. So that's how I'm drawing here. The dotted lines on the back side, and so here our 6 bonds are already shown. Out of the 6 bonds, now if you want to show the isomers, it has to be an optical isomer like this. Keep on drawing the ligands as I'm drawing here, mention N every time, and every time is given here, and a line joining this. And now draw the mirror image of the same complexes as we have drawn in the first one. So again I'm drawing the 2 bold lines, 2 dotted lines, and the mirror image of this. So this is how I'm going to draw the mirror image. This is exactly same as the opposite one here. So drawn N and with a line. So these are the two isomers drawn, stereoisomers shown. Next part, it says shows another ruthenium complex. So this is a ruthenium complex. You can see that ruthenium is here on both sides of one of the benzene compound. We can't say benzene, but it's a substituted benzene kind of a compound with 6 rings, but it has, rather than 6 carbon, it has got nitrogen. So obviously it's in another form. This complex contains a neutron ligand pyrazine. Pyrazine is another ligand here, it's shown here. So the ruthenium is bonded to this pyrazine ligand here. And the question comes is, suggest how pyrazine is able to bond to 2 separate ruthenium ions. Now the question is actually says that why only one pyrazine can bond with 2 of the ruthenium ions, because you can see that one ruthenium ion is bonded to one of the nitrogen and the second nitrogen is bonded to the second ruthenium ion. So why is this so? Because both the nitrogen have the lone pair which can form a dative bond with the ruthenium ion. So as simple as that, we can say that pyrazine have two nitrogen atoms, or you can say only nitrogen also, with lone pairs of each nitrogen. With lone pairs of each nitrogen can form dative bonds with 2 ruthenium ions. So simple as that it has got 2 nitrogen with lone pairs each, and both these nitrogen can donate its lone pair, one of the lone pair, to the ruthenium ion, forming the dative bond, and so 2 ruthenium ions are bonded to it. Now pyrazine is an aromatic compound. The bonding and the structure of pyrazine is similar to that of benzene. Describe and explain the shape of pyrazine. In your answer, include the hybridization of nitrogen and carbon atoms, how orbitals overlap, forms pi bonds between the atoms in the ring. Now let's understand what is exactly, as they have asked about, they have given an information about the bonding and structure of pyrazine. The bonding and structure of pyrazine is just like a benzene, and what is asked is the hybridization of the nitrogen and carbon at least, and how the orbitals overlap, form pi bonds between the atoms in the ring. Now if you talk about the hybridization, structure and bonding of pyrazine, then if we draw a structure like this, we have nitrogen. Obviously such a structure is hexagonal. Can we see it's an hexagonal structure with 4 carbon in the ring and 2 nitrogen. So we can describe that bonding here, that there are 2 nitrogen atoms and 4 carbon atoms forming an hexagonal ring, forming a hexagonal ring. Just like benzene, it's forming an hexagonal ring with alternate double bond, but we don't need to mention it here. Now it's forming an hexagonal ring. The hybridization, if it's having double bond alternate, that should each carbon and each nitrogen is forming a double bond. So hybridization of nitrogen and carbon, each, both the elements have sp2 hybridization. The hybridization of nitrogen and carbon is sp2 hybridization. That's how I'm writing here. Now if they're talking about how orbitals overlap, form pi bonds between the atoms in the ring. Now we can see that both nitrogen and carbon are p block elements, so they have p orbitals in their outer shells. So both these p orbitals of nitrogen and carbon, they are overlapping sideways. So we can write that the pi bonds are formed, the pi bonds of nitrogen and carbon are formed by sideways overlap of p orbitals of nitrogen and carbon. So this is how we describe it. We have included both these things here, and plus we have described the structure of the ring also here. So let's go ahead with the next part here. Next part is predict the number of peaks seen in carbon-13 NMR spectrum of pyrazine and explain your answer. Now, if you are talking about carbon-13, we have to look at the environment of carbon only in the ring. So again, as we have already discussed, there are 4 carbon in the ring. So out of these 4 carbon, how many carbon are in different environment, and accordingly they'll form give different peaks. But here if we can say that each carbon is having a double bond, each carbon is bonded to a nitrogen, and each carbon is bonded to 1 carbon and 1 nitrogen. So you can say that each carbon is bonded to 1 carbon and 1 nitrogen. So you can say that all the 4 carbon are in the same environment, and so it's going to give only 1 peak. 1 peak is shown in carbon-13 NMR, and the reason is that as all the carbon atoms, all the 4 carbon atoms are in the same environment. As we have already discussed why all the 4 carbon atoms are in the same environment, so it's going to give the same peak, that is only 1 peak. So this is how we are going to explain it. Give how many peak, and also explain. The next part is the overall charge of the ruthenium complex in figure 4.1 is 5+. Figure 4.1. So above what we have already seen. Deduce the possible oxidation states of 2 ruthenium ions in the complex. It says overall charge is 5+. Now let's have a look at the complex which is shown here. Overall charge is 5+, and deduce the charge of ruthenium in both the complexes. So what are the chances? So let's understand the whole structure of this complex. Here we can see that there are 5 ammonia ligands bonded on both sides. Now ammonia ligands is having a charge neutral. It's a neutral charge, so 0 charge. Nitrogen, and for the pyrazine also it's written it's a neutral ligand. So even pyrazine doesn't have any charge. It's a neutral ligand. So whatever charge of 5+ is given, that's only because of the ruthenium. So if we talk about the ruthenium's charge, it should be either +3 and +2, or it can be +4 and +1. Then only we can have a total of 5+. So you can write either of it. So we are just writing directly the possible oxidation states of +3 and +2. This is how we are going to end up writing the charge. Now let's go ahead with the 6th C sub question. It is osmium tetroxide. Osmium tetroxide formula is given here. Reacts with the alkenes in a similar manner to cold dilute acidified KMnO4. Reacts with alkenes in a similar manner to cold dilute acidified KMnO4. Now figure 4.2 shows a proposed synthesis of the condensation polymer G, and the condensation polymer G is written here, and here is the starting ring structure. Step 1 is where carboxylic acids of the benzene undergoes acylation to form a chloroacyl compound. So suggest a reagent for step 1. Now step 1, what's happening? Carboxylic acid is changing to acyl chloride, and the chlorinating agent is obviously POCl5 or SOCl2. At the normal room temperature, these are the 2 chlorinating agents that can chlorinate the carboxylic acids. The next part is draw the structure of the exact 1 repeat unit of the condensation polymer G, and the ester linkage should be shown fully displayed. Now let's understand how the condensation polymer is formed. Here we have in benzene structure with the acyl chlorides, 2 acyl chlorides, that is polymerizing with one of the alkene. Now it's written alkene. Osmium O, that is OSO4, reacts with alkenes in a similar manner to cold dilute acid KMnO4. that shows that a diol should be formed on this ring structure. So let me draw that diol structure here. It's an hexagonal ring again with OH as shown here, because the cold dilute acidified KMnO4 will react with alkene forming a diol. So if osmium tetroxide is also reacting, it should form a diol. Now if these two are forming a condensation polymer, it's going to remove chlorine here from and H here from the both sides, and this is how it's going to form the condensation polymer. So if we draw one repeat unit, if we start with one of the benzene structure first, then I'll write CO first and then extended bond here, again CO first and then the extended bond and the ring here. Now that forms an ester with the alkene shown here, which is again an hexagonal ring. So I've drawn an O of the diol, that is alcohol, and again an hexagonal structure. So if I draw an hexagonal structure, it should end up, this is how I'll draw the hexagonal structure. Now remember, this second ring is not like a benzene, should not have an aromatic ring inside. So this is how I'm going to draw the one repeat unit of the condensation polymer G. So here is one extended bond and here is the second extended bond, and this is the one repeat unit. Now I've drawn the double bond O on the top, but you can draw it in the down here, because here I've written it down. But yes, this is the repeat unit, and here we end with the question 4.